자, 우리 지난 시간에는 Continuous Time Finance를 이해하는 데 필요한 수학적인 툴들을 배웠죠? 그럼 그 수학적인 툴들을 이용해서 어떤 식으로 이제 Continuous Time Pricing Equation들을 유도해낼 수 있는지 이번 시간에는 보겠습니다. Continuous Time Method를 이용해서 파이낸스를 배워나가는 과정이라 할 수 있죠. 물론 이제 오늘 렉처를 이해하기 위해서는 이제 Continuous Time Method에 대해서 잘 미리 숙지를 하고 있어야 됩니다. 자, 그럼 이제 들어가 보도록 하죠. So today's lecture is going to be about the continuous time finance. So we will use the techniques that we learned in the last time. In other words, continuous time mathematics. And we will see how the basic pricing equations can be obtained using continuous time math. Okay, let me share the screen. Okay, so the first step is to define how the instantaneous return on a security can be expressed. Okay, so let's begin from the discrete time analogy. So in a discrete time, you can view in the following way. So return in a discrete time is going to be okay, so this is going to be net return. Let's just suppose there are dividends as well. 디비den드까지 있다면 이게 net return이 되겠죠. 어떤 주식에. And we can rewrite it as PT, delta PT plus 1 over PT plus DT over, I'm sorry, the dividend should be in the next period. Okay, in this fashion, right? So in a continuous time, this is going to be plus, okay, because the delta T, which delta T is actually 1 in a discrete time setting, and this goes to 0. And in that case, oh, I'm sorry, that should be DT. So the instantaneous total return on a security, I mean total return because it incorporates dividends. 토탈 리턴이라고 부른 이유는 디비den드까지 포함해서 그런 겁니다. 따라서 이제 total return can be expressed this way. This price process in a general form will be given like this. So we will assume that the expected return is going to follow some value, means some arbitrary value, okay, plus some shocks. And then we can write it in this fashion, okay, here you're assuming the dividend to be 0, right? Okay. So when you have the price process in this fashion, 네, 그래서 price process가 이렇게 geometric Brownian motion이나 log normal process로 주어졌을 때 이런 식으로 이제 주어지게 되는 거죠. 그래서 이제 so as a one example, we can consider the geometric Brownian motion in constant drift and volatility. In such case, the return process, instantaneous return process, is given in this fashion. Okay. So, and we learned in the previous class that when that is the case, price PT is simply current price plus mu minus sigma squared T plus sigma dz minus d0, and usually we assume that the time zero value of the Brownian motion is simply 0. In this case, PT is P0 e to the mu minus a half sigma squared times T plus sigma Ct. Okay, and then we also learned that expected value of PT is going to be P0 times mu T. Okay, so this is what we learned last time. Another important asset class is so-called money market account. Money market account, you can view them as the bank deposits or some risk-free asset. So when the special thing about the money market account is there's no randomness. In other words, so the value of the money market account at some point is current time times RF. So here we're assuming that the expected, the risk-free rate can vary over time. In that case, from T to capital T, RS, F, DS. And you can easily check by taking the derivative of M, and then you will see, you will obtain this formula here. Okay, so we are given with the basic assets. So once we have these assets, now we can, going forward, for obtaining the pricing equation. For that, we need to define the utility. Okay, so we define utility in the following way. So to see why the utility can be defined this way, let's first consider the discrete time case. Okay, discrete. In the discrete time case, utility of the investor who lives infinite period of time can be viewed in the following fashion. Current consumption, C0, plus delta. Next period consumption here, delta is, delta is not good. Oh. Okay. Let's just assume that the discounting is done by some continuous compounded rate delta, so that actually there's a typo. There should be negative sign here. So this is a typo. Okay, so if you consider a discrete time case, then your investor's utility is going to be infinite sum of the utilities going forward. And of course, you will need to take the expectation, right? And the continuous time analog of this thing is, okay, let's just continuous time. Continuous time analog is simply U is, right? So it's just the sum of all the future utilities. That's going to be integral from time t equals 0 to infinity and discounted utilities and take the expected value. Okay. So that is going to be a continuous time analog of the utility function. So given that, let's do the pricing in a continuous time. Okay, and we will obtain the Euler equation here. Euler equation that we learned in the basic pricing part 1. So how do we do that? Solving the Euler equation in a continuous time infinite horizon involves the dynamic programming. So instead of doing that, we will use the perturbation method here. So let's suppose the optimal consumption path is CT prime. So that is the after investors optimization problem. And we will further assume that there's a small perturbation of psi at time t by purchasing the security with price PT. So what is the, so let me give a more concrete example. So what is going on? Okay, so let's consume the a discrete time example. Okay. In a discrete time, suppose the investor has the following. Investor has to maximize the utility, infinite horizon utility, which is basically expected value of all the sum of the utilities okay, this goes from S. Let's just write it in terms of S minus delta S mu C as well. Okay. So that's the investor's maximization problem for all CT. Okay. Now suppose investor has done it and the investor, the agent knows the optimal consumption path. Okay. Optimal consumption path is CT star. Okay. T0 to infinity, right? In other words, after the optimization, the investor's optimal consumption path is given like that. Okay. So that is going to be expected value of mu C0 star plus e to the negative delta u C0 star and C1 star and so on, okay, to the infinite time. Now let's just suppose at time t, investor is going to deviate a little bit from the optimal path, okay, by doing what? By purchase the financial asset whose price is PT. So they purchase an asset whose price is PT. Okay, purchase Xi shares of an asset PT of PT, okay, which is going to give you the future dividend streams. That will give you the dividend streams of dt plus 1, dt plus 2, and so on for infinite horizon. Okay. When that is the case, what is the utility loss? The utility loss at time t. Okay? So by saying the utility loss, meaning that the investor is at the optimal, the investors are just so happy with the current level of consumption. Now investor is going to consume less, but instead with the fewer amounts of money, the investor is going to purchase the financial asset. 자, 무슨 말이냐면요. 좀 정리를 해드릴게요. 자, 에이전트가 있고요. 인베스터가 있고 이 인베스터가 CT라는 컨섬션 스트림을 통해서 옵티멀 컨섬션을 하고 있다고 가정하고 있습니다. 그런데 이제 이 옵티멀리티가 어떤 상황에서 만족되어야 하는지를 보기 위해서요. 이 인베스터가 옵티멀리티에서 살짝 디비에이트 한다고 보는 거예요. 어떻게 해요? 파이낸셜 에셋을 그 사이 쉐어만큼 사는 거예요. 그 사이 쉐어만큼의 파이낸셜 에셋을 사서 가격 PT를 지불하고 이렇게 되면 이제 현재 컨섬션이 줄어들게 되죠. So there's going to be utility loss. Why? By purchasing the asset, current consumption CT is going to be low. Will be low. By how much? 얼마만큼 낮을까요? By how much? That amount is going to be given by the marginal utility of your consumption at optimal consumption at time t, right? So that measures, that marginal utility measures the change in consumption, change in utility when you change your consumption by a unit. 이게 이만큼이 바로 utility loss예요. 1원만큼 우리가 consumption을 줄였을 때요. But then how much of consumption are you reducing? You're reducing because you're buying XI shares of the financial asset by paying the price PT. So that's going to be your utility loss at time t. 즉 time t에서 현재 소비를 줄이고 줄인 만큼 얼마만큼 줄이죠 소비를? XI times PT. PT라는 가격을 지불하면서 XI만큼의 파이낸셜 에셋을 사잖아요. 그만큼이 컨섬션이 줄어드는 거예요. 그럼 그만큼 컨섬션에 대해서 유틸리티는 얼마만큼 줄까요? 마지노 유틸리티를 곱하면 되죠. In other words, you multiply the marginal utility with the amounts of assets you're purchasing and the price, you get the utility loss. Now, what is the whole point of reducing your utility at time t? By purchasing the asset. If you purchase the asset is going to pay you off dividends in the future. Therefore, your utility in the future is going to be greater. 즉 무슨 말이냐? 왜 지금 이 파이낸셜 에셋을 구매를 할까요? 이 파이낸셜 에셋을 구매함으로 인해서 미래의 디비던드가 늘어나게 되고 따라서 미래의 유틸리티가 늘어나게 되는 거죠. 미래 컨숨을 더 할 수 있으니까. 즉, how much of utility gain we're getting after time t plus 1? In other words, what is our utility gain? Utility gain is going to be, again, marginal utility next period times xi times dt plus 1. 왜냐하면 이 financial asset이 디비던드가 나오잖아요. 다음 피리어드에. 이 디비던드가 얼마만큼 나오죠? xi만큼 나오죠? 이만큼을 내가 더 소비할 수 있잖아요. 따라서 marginal utility를 곱해야 되죠. So that is the utility gain in the next period. And this utility gain needs to be discounted. But then this is not the end of the dividend. There's another dividend, right, in the next period, which is at time t plus 2, you get another dividend. And this dividend is going to be discounted at this rate. And there's also the next dividend 인피니트한 거죠. 따라서 in equilibrium, in other words, the fact that the investor is optimizing the consumption path, meaning the investor should be indifferent between the loss and the gain. In other words, utility loss should be the same as the utility gain. 즉 utility loss와 gain이 같아야 돼요. 그게 indifference condition이거든요. 그때가 바로 인베스터들이 그들의 consumption path를 optimize 하고 있을 때입니다. 따라서 어떻게 되냐? U prime, what is the utility gain? Sorry, utility loss should be the same as utility gain. let me just write it using the sigma. Okay. Sum of all the future s from 1 to infinity, 1 to infinity, e to the negative s delta, right, times dividend times c. Okay. Now we have psi, same thing on both sides, divided, and we have the following optimality condition. Okay. Of course, we need to have expectation. Okay. Expected value of infinite sum e to the minus L delta u s t plus s psi. Here, s star dt plus s. Okay. Now, how can that be expressed in a continuous time? In a continuous time, we have the following, and we have the integral with respect to. So we have integral with respect to s 0 to infinity e to the negative s delta u c t plus s ds. Okay, of course, there should be expectation. Okay. So this is the optimality condition, and that's what we have here. Okay. So intuitively, this is what's going on. Now, suppose the investor is at optimal. 인베스터가 이제 optimal path를 정한 거죠. CT가 이제 인베스터한테 가장 optimal path예요. 이 optimal path란 말이 무슨 말이냐면, 이 optimal path에서 그 사이만큼 내가 perturbation에서 deviate 하잖아요. 그러면 optimality condition이란 말은 이만큼 deviate해서 얻는 benefit과 loss가 같기 때문에 인베스터는 indifferent하다는 얘기예요. 둘 사이에서 아무 차이가 없어야 됩니다. 즉 loss와 gain이 똑같아야 돼요. 그 말이 무슨 말이냐? 내가 만약에 이 컨섬션에서 그 사이만큼 deviate 한다고 해봅시다. 어떻게 deviate 하죠? financial security를 사요. financial security를 삽니다. Once you buy the financial security, by how much? By psi. And how much do you pay? PT. So PT times psi is the money you pay to buy the financial asset. And 그만큼 이제 consumption이 줄어드는 거죠. In other words, your consumption decreases by CT times DT. So this is your current consumption minus PT times sigma. PT times sigma is the money you're spending to purchase the financial asset. So that is the current utility loss if you multiply it by the marginal utility. 저 quantity가 바로 utility loss입니다. 즉 내가 지금 PT 곱하기 psi는 컨섬션을 줄이는 만큼이죠. 컨섬션을 그만큼 줄였고 거기에 마지널 유틸리티를 곱하면 내가 유틸리티가 얼마만큼 줄어드는지 알게 되는 거죠. Now, once you do this, there's benefit. What kind of benefit do you have? The benefit is that this financial asset is going to pay dividend stream in the future. By how much? By this much. Now, the fact that you are at equilibrium, investor가 equilibrium에 있단 말은 gain and the loss have to be the same. Therefore, we obtain this pricing equation in a continuous time. Okay. Okay, so now from the previous pricing equation, it's easier in a continuous time define the stochastic discount factor, I mean pricing kernel. Let's just call it pricing kernel. Pricing kernel in this fashion. discrete time 때랑 조금 다르죠. discrete time 때는 우리가 pricing kernel을 m이라고 define 했고 이렇게 정의했잖아요. 즉 여기서 보면 여기 마지노 유틸리티를 컨티뉴어스 타임에서는 이걸 그냥 디스카운트해서 정의를 해줘요. So it's a little bit different in the continuous time because if you define pricing kernel in this way, it's much easier to do the calculations. Okay? Now, if you define it this way, then the pricing equation in the previous slide becomes like this. You do the derivation yourself. 직접 해보세요. Derivation. Okay? Now, once you have this, and you can obtain the pricing equation in this way. So how does that work? How does that work? So from the basic pricing equation in a continuous time, okay. Now let's take the difference. How do we take the difference? We're not going to use the Ito's formula here, but instead we will use the following. We will use we will just use the so we will take the difference on both sides and d of the entire thing here, right? Copy, paste. Okay, so this is what we're going to do, and we will use the definition of the delta. In other words, so this is the same as okay, it becomes like this. 자, 이렇게 되죠? 똑같은 식으로 지금 유도를 하고 있습니다. Now let's take the expectation at time t on both sides. 양변에 conditional expectation을 다 취해 줍시다. 그럼 어떻게 되죠? Conditional expectation of delta pt lambda pt equals 이렇게 되죠? Okay. 이렇게 됩니다. Now we use the LIE. What is LIE? That is, if you remember from the first class, law of iterated expectation. Law of iterated expectations. 이게 어떤 거였죠? 즉 뭐였죠? 이게 expected value of something when s is greater than t is simply expected value of the thing, right? So if you look at here, this is simply dpt lambda t equals, now if you look at this too. This is where you're using the law of iterated expectations. In other words, you get the following expected value of s equals. Now, what the law of iterated expectation means is that this expectation is just going to disappear. Okay, it will just disappear so that you get only the remainder. Copy, paste. Okay, and it will also disappear. It becomes this way. Now, we will substitute in this fashion. Okay, so s prime. So we will substitute dt plus s as the s prime, and you get conditional expectation at time t. And this is going to be s prime equals, when s is 0, s prime is going to be dt 0, s prime plus dt. This is going to be t plus s prime d t plus s prime ds prime minus s equals 0 to infinity. Okay. And in there, the calculation is a little bit complicated, but this is doable. Now, you can just simply rewrite it in this way. Copy. Paste. What am I going to do? Okay, it doesn't matter whether you have prime or not. Okay, therefore, this is going to be s equals dt to the 0, t plus s, dt plus s ds, and this is negative of expected value s equals 0 to dt, t plus s. Okay, and then we have the pricing equation, right? This is basically negative of lambda t dt. Okay. Therefore, we have lambda t dt plus expected value of dpt lambda t is 0. Okay? So we have the equation here. So this is the fundamental. I'm sorry, there should be dt. This is the pricing equation for the continuous time case. Okay? The math is a little bit complicated, but this is doable. And when you have time, it's a good exercise to follow this. Okay? 자, 따라서 이제 continuous time에서 여기 나온 이 식 있잖아요. 이게 basic pricing equation이 됩니다. Okay. Okay. 그러면 이번 렉처는 여기까지 하고요. 이 다음 렉처부터 이 continuous time pricing의 basic equation이 어떠한 의미를 가지는가에 대해서 보도록 하겠습니다. So in the next lecture, we will give meanings to the continuous time version of the pricing equation.